Okay, so uh, when you saw there at the end of the last clip, we were talking about taking repeated samples from the same population. All right, so again, imagine that bag of chips, and you are drawing randomly 8 chips from that bag over and over and over again. All right, so let's say that you have 100 samples, all of the same size, sample 8. Now, some of you may have caught the fact that we are putting those chips back in the bag, and so it's possible that one or more chips may be drawn twice. In fact, if we actually did that 100 times, more than one chip might be drawn several times, for example. But that's okay; doesn't matter. So once we have those 100 samples, all right. Now I hope you're envisioning with me what this means. Once we have those 100 samples, each of the same size, 8 chips each, we could calculate a mean for each of those samples. All right, we could calculate a mean for each of those samples. So if we had 100 samples and we calculated each of those samples means, how many means would we have? We'd have 100 means, right? So now we have 100 means, and we could plot those means in a frequency distribution. If we did that, that distribution would actually look pretty normal. It would approximate the normal probability distribution. So in essence, and this is really, if this is confusing, go back and watch this again and see if that helps. But essentially what we're doing is we are shifting the unit of analysis. We're shifting the unit of analysis from the case to the mean. So in other words, we're no longer talking about analyzing cases, or at least we're not talking about analyzing cases right now. We're talking about analyzing means. So instead of 100 cases, you've got 100 samples, and you've calculated a mean for each of those samples. So now, in addition to having 100 samples, you've got 100 means, and that's what you're concerned about, the 100 means. If you were to plot those means in a frequency distribution, the shape of that distribution would be normal, and here's where the real magic comes into play. The distribution of means would appear to be normal even if the original distribution of scores from which all those samples came from was not normal. Now there's a very specific principle, or theorem actually is what it's called. There's a very specific theorem. It's called the central limit theorem, and it's a theorem. It's a mathematical theorem, and it holds true, a statistical theorem. We will come back to this, but the main thing I want you to get, all right, per the supplemental handout, which I hope you have downloaded. What I hope you get is that we've shifted the unit of analysis from the case to the mean. Our unit of analysis is the mean. All right, we'll come back to this in a little bit. In the example I just gave you, or the set of circumstances that I just tried to walk you through verbally, I asked you to assume a sample size of 8. All right. In other words, our sample size was fixed, a sample size of 8. If we were to do that same exercise, but changed the sample size to say instead of a fixed sample size of 8, assume a fixed sample size of 9 or 10 or 15 or 20. So instead of, say, a sample size of 20, so we've got our big bag of chips, and we reach into our big bag of chips 20 times and we pull out 20 chips. That's our first sample. All right, and we calculate a mean from that sample and we toss them back in. And we shake up that bag and we take out a second sample of 20. Again, the sample size is fixed, sample size of 20, and we calculate a mean and we throw those chips back in. And we shake up that bag again and we take out a third sample of 20 and we calculate a mean and we throw it back in and we shake up that bag and we take out a fourth sample of 20 and calculate that mean. If we did that for different sizes of samples, 8, 9, 10, 20, 30, the sampling distribution for each fixed sample size would approximate normality, but here's the best part. Here's the most awesome part. is that the shape of the distribution would become more normal as the sample size, the fixed sample size, increases. And I have a drawing in your supplemental handout that approximates that. And that's this drawing right here. Those are 1, 2, 3, 4 different curves. And as you can see, or as I hope you can see, each sample size, or excuse me, each curve is approximately normal, but the extent to which the curve becomes more normal increases with increased sampling size. So for example, a sample size of 8, looking at the drawing that I just held up, if you're looking at that curve based on a sample size of 8, it's normal, right? It's symmetrical, it's kind of bell-shaped curve, but it's flatter than it should be, right? It's not as peaked as it should be. Well, move up to a sample size of 10. Again, we have a curve that's kind of normal, it's bell-shaped, it's symmetrical, but it too is flatter than it should be, but it's more normal than 8. Now look at a sample size of 20. It's bell-shaped curve, it's symmetrical, but again, it's a little bit flatter than it needs to be. And then finally, when we get to a sample size of 20, or a sample size of 30, we've almost approximated the exact normal curve. So again, looking at that drawing, 8, 10, 20, 30, with each increase in fixed sample size, the theoretical probability distribution for the mean becomes more normal. And that's the takeaway, as you can see at the bottom of that drawing. The takeaway is the larger the sample, the more normal the sampling probability distribution. I'm going to say that again. The larger the sample, the more normal the sampling / probability distribution becomes. Now, we have talked about this before. You may recall that I mentioned this before in class, and I said it was going to come up again. Well, guess what? It's going to come up right now. The reason that the sampling probability distribution becomes more normal with increased sample size is because there is less, can you guess what I'm about to say? It starts with an E, because there's less error. There's less error in the samples, right? If you have a sample size of 8, or to use the example of today, a fixed sample size of 8, there is more error in that sample than there is a sample size of 30, right? There is an inverse relationship. An inverse relationship, they go in opposite directions. There's an inverse relationship between sample size and error. The smaller the sample size, the more error. The larger the sample size, the less error. And we're approaching a point in the semester where we're going to demonstrate that literally. All right, so think about that. And again, if you need to rewatch some of these segments, feel free to do that. Now, once our theoretical, there's that word again, theory. Once our theoretical sample size reaches 30 or more, the sampling / theoretical probability distribution is virtually indistinguishable from normal, meaning the normal probability distribution, or the Z probability distribution, which we have been working with extensively, as you can see from the handout, if you're following along with the handout. So think about this. We're no longer talking about the population, all right? When we were working with the Z probability distribution and the Z table, when we were working with the perfectly normal probability distribution, we were dealing with the population. We were dealing with everything, right? And what is a population again? It's every single thing of something that you're interested in, right? So if we have an entire population, how much error do we have? If we have an entire population, how much error do we have? We have none. None. And we don't have to deal with statistics because we're dealing with parameters, and parameters don't have any error, right? Now that's Z. That's the normal probability distribution. We're no longer talking about Z. As you may have guessed, if you are a guessing person, we're getting ready to move into our next probability distribution, and that is a probability distribution that takes fixed sample sizes into account. Sample sizes of 8, 9, 10, 15, 20, 25, 30. But once we get to 30, we are virtually indistinguishable from normal, and that's the beautiful thing about the mean. Thus endeth segment 2.